Okay, so when you're solving exponential equations, ideally we would try to change to the same base like you would have done in 3U. So in a question like this, I look at these values, and if I don't have to use logs, I'm just going to solve it as I normally would with an exponential and see if I can change to the same base. Right, so I know that 16 is a multiple of 2, so I could change that. And the fifth root of 2 is also a multiple of 2. So that would be 2 to the 1/5. And then I have two bases multiplied together. I could add those exponents. So 4 plus 1/5 would be 21/5. And then now that I have the same base on each side, I can then say, okay, then x equals 21/5. Okay, so that's how we would normally do it. Change the same base if possible, and then evaluate from there. Sometimes we cannot change to the same base. So this is where we are going to use the change of base formula for some of these. So the change of base formula is useful when I have a question like this, 3 to the power x equals 11, and I cannot change to the same base. And it might be in this form too, down at the bottom here. It might be in log form. Log base 5 of 23 equals x. So that's asking me 5 to what power gives me 23. Well, I can't solve that in my head because it's going to be a decimal answer, right? 5 to some power to give me 23. So when we cannot change to the same base, we want to inverse an exponential function by using logs. So remember that logarithms undo exponential functions because they are inverse operations. So I start by logging both sides. Then I'm going to use my power rule, which I learned in laws of logs, and I want to solve for x. So I'm going to bring down the x from the exponent down to the front because I want to isolate for x, so it needs to come down. And then I will isolate for x by getting rid of the log 3 and dividing on this side. And then I can just type this into my calculator because I've changed it from log from 3 to the x equals 11. I've changed it to logs, which are log base 10, and that means I can then use my calculator because I have log base 10 on my calculator. And so I just type in log 11 divided by log of 3. And I get an answer of 2.18. And I can use as many decimals as I want, depending on how accurate I want. So that means that 3 to the power 2.183 should give me an answer close to 11. Okay, so that's what I've found. This is called the change of base formula. So I'm changing the base from base 3 to logs. And I can go through this process, or I can go directly to my log formula. So the change of the base formula says that we can take log of the result divided by log of the current base and find our answer. So for example, I want to find x. I would take log of the answer, log 11, divided by log of the current base, log 3, and that will give me my answer. If it's in log form, I would take log of the argument or the answer, which is 23, divided by log of the base, which is 5, and that will give me my answer. And I can go directly to my calculator to evaluate this. And I get a value of 1.948. And then I can check it. I can check, is 5 to the power 1.948 equal to 23? So we'll just check. And we get an answer of 22.99. So that's pretty darn close. Okay, so that's the change of base formula. If it's in exponential form, like this one, I can find x by taking log of the answer, 11, divided by log of the base, 3. Or if it's in log form, I can take log of the answer or the argument, 23 divided by log of the base, which is 5, and then just type that into the calculator. If you can't remember the change of base formula, your go-to is always, well, log both sides, bring down the exponent, isolate for x, okay? So it's not necessary to remember this formula, but it's helpful when you're solving. Okay, so that is the first part of, I think that's, I can't remember what section that is. There is a section on estimating. So before we actually solve, I think it's 8C. So box 8C would have been finding the answer by estimating like we did in 3U. So that's not going to be evaluated, but it is in the guide. So 8C is estimating. And then this here is 8D, I believe. And this is just some information about natural logs. Again, you're not going to be evaluated on this. It's just telling you the difference between a common log and a natural log. So a common log is the log that we use on our calculator, and that is base 10, okay? A natural log uses just a different base. It's called E, and it has this value. So you can see this big long decimal. It's much easier to use 10, right, than 2.71828. So we generally use the common log. You're going to get the same answer either way. The natural log on your calculator would say ln, right? That's what it looks like. And that is the Latin word for natural log. So the Latin word is Logarithmus naturali, or ln. So that's why it's ln and not nl. So that is pronounced as ln, like a lawn. And you can use it as well as the regular log. So if I wanted to do that same question, 3 to the x equals 11, I could do log 11 divided by log 3, or I could do ln 11 divided by ln 3, and I would get the same result. Okay, so it's done no differently, it's just a different base. You tend to use ln a bit more in calculus. They use it much more in business and biology. We do some business stuff in calculus, so that's why we use it a bit more in calculus, okay? So that's just some information. So 8C and 8D are nothing that will be on any of the tasks or tests, just some things that you can kind of read through. Okay. Then we come to some questions that are in log form that we want to solve. So our first option was change into the same base. Our second option is put it in exponential form if we can. So in this first question, I'm going to put it in exponential form in order to solve it. So I have base 4 to the power 1.8 equals x, and I can easily type that into my calculator and find the result. So if you can solve by just putting it in exponential form, then that's what you're going to do. Okay? Same with the second one here. I know log has a base of 10 because there's no number there, but it's a 10 because whenever there's not the number, we assume it's a base 10. So it's log base 10 to the power 2 equals the argument, which is 2x plus 10. And I can solve that just by isolating for x. And easily solved. Okay, so that's my first plan of action. Can I put it in exponential form and solve it? If the log is not isolated, like the top question, you want to get it by itself. Okay, so I'm going to move the log to the right side. Then I can put it in exponential form, so it's base 10 to the power 1 equals 2x, so x equals 5. In the second question, I can again put it in exponential form. I have base 3 to the power 2 equals 3x plus 7. And then we can solve. And we get our result. Okay, so that's pretty easy. Easy peasy. Okay, you're going to get some questions where you have more than one log on the either side of the equal sign. So if you have more than one log, you can't put it in exponential form until you get one log. And so we have to use our laws of logs sometimes to combine before we put it in exponential form. Okay, so this one has log base 5 minus log base 5. So same base, so I can combine these using my log laws and change subtraction to division. So I'm going to combine those two logs to make 1. And now I can put it in exponential form because I have one log. So it would be base 5 to the power 1 equals my argument. And then I'm just going to cross multiply. So remember 5's over 1. So if I cross multiply, it's 1 times x equals 5 times x minus 2. And then I'll expand brackets. I'm going to put the x's to the right. So 5x minus x is 4x. I'll put the 10 on the left. And then I can solve for x. So you can't put it in exponential form until you combine the logs so that you have one log. So in this second question, we have two logs on the left that are added together. They are the same base, so we can combine them. So we're going to change addition to multiplication. Once I have one log by itself, I'll put it in exponential form. So base 2 to the power 3. And then we'll expand brackets. Now, in this question, I have a power 2. I have a quadratic. So in order to solve, I need to factor. So I'll need everything on one side so that it equals 0. So I'll put the 8 on the right, and now I have a quadratic. I can factor it. So 4 2's are 8. And then we take each root and solve for x. Okay, so that leads us to checking for extraneous roots. So what is an extraneous root? An extraneous root is a root that is not possible. So it's an answer that is invalid. So if we think about logs, especially when they're in exponential form, so let's just put a new screen here. So if I had, let's say, 3 to the power x, and I'm looking at the answer, this result cannot be negative. Right? The argument can't be negative because I can't have 3 to a power and get a negative result. That's not possible. Right? Because if you think of our numbers, 3 to the power 1 obviously gives me a positive result. And as that number gets bigger, I get a bigger number. 3 to the 0 is 1, so that's still a positive result. 3 to the negative 1 is 1/3. Right? So even when the power is a negative number, I'm just getting a positive fraction, right? That result will never be negative. And if you think of your log graph, right, we don't have any negative values here. So that's what an extraneous root is. When you look at your answer, you're going to take your solutions and put them back into, let's do it here, into the original question and make sure that that's not a negative result. So if I put in -4 here, log base 2 to the -4, well, that's not possible. I can't have 2 to a power and get -4. That's not valid. And if I put it in here, -4 plus 2, well, that gives me -2. Again, that's not possible. 2 to a power and get -2, not possible. So I would say x equals -4 is an extraneous root, right? It's invalid. So that answer is not a valid answer. If I put 2 in, 2's okay. Log base 2 to the 2, well, that equals 1. That's okay. And then if I put it in x plus 2, that gives me 4. 2 to the power 2 gives me 4, so that's okay. So x equals 2 is a valid root. X equals negative 4 is not. Okay, so you have to identify the roots or solutions that are not valid. Okay, the next one, we have 2 logs added together. So we're going to combine them. So addition is going to become multiplication. Once I combine them, I can then put it in exponential form. And then we will expand brackets. It's a quadratic, so let's get everything on one side. And then we'll factor. So 9 times 4 is 36. It'd be minus 9 plus 4. And then solve for our roots. So x equals 9. And x equals negative 4. And then I check for extraneous roots. So 9 is okay. 6 to the power something gives me a positive result of 9. That's okay. And then 9 minus 5 is 4. That's okay. It's a positive result. So 9 is okay. Negative 4 is not, because I can't do log base 6 to some number and get a negative 4. Not valid. Okay, so this is an extraneous root. So my solution would be x equals 9. Okay, just let me see if there's any questions on that. Oh, maybe. Okay, Dylan, you back on? Okay, hopefully, sometimes if things technologically are not working, it's good to log out and log back in, and then sometimes it works. Okay, so let's look at this one. Same thing, I have 2 bases on the left. I'm going to combine them. So subtraction is going to become division. The value on the right is already in log form, so that's fine. I don't need to change that. If I have the same log on the left as the right, it's kind of like an exponential equation. If you have the same base, you don't need the base anymore. You can just drop it and then solve for the argument. So I will cross multiply. So I get 12 equals 3x, divide by 3, x equals 4. And then I check and make sure that that result is valid. If I sub it in there, I have a positive result, so that answer is fine. Okay, so sometimes the result might be in log form and not as a number. Okay, if you have questions like this that are not in log form and we cannot change the same base, we're going to do exactly what we did previously. So in that very first question, right, what was our strategy? We logged both sides, right? If we couldn't change 3 and 11 to the same base, we logged both sides. So that's what we're going to do here. Our first strategy is to log both sides because we want to undo the exponential function. So we're going to log the left and we're going to log the right. Okay, our next strategy will be to bring down the exponents, right? We want to solve for x, and the x is in the power in the exponent, so it needs to come down, and then this one needs to come down. Make sure you put it in brackets. Once we've done that, we're going to expand brackets. So that's why we needed it in brackets, because it applies to both terms. So we're going to multiply out our brackets. So 3x times log 2 minus 2 times log 2, and then x times log 5 plus 1 times log 5. And then it just becomes a simple solving. you want to solve for x, so that means you need to isolate for x. So any terms that contain an x need to be on the same side. Does not matter which side, and I'll do both. I'm missing a 2 there. I'll do both ways. So the first way, I'm going to put the x's on the left. So that's going to come here. This x log 5 is going to come to the left. The log 5 stays on the right, and then we'll move the 2 log 2 to the right. So any term that contains an x is on the left. Any term that does not contain an x is on the right. Then I'm going to factor out the x because I want to isolate for x. So I'm just going to take the x out, nothing else. So that leaves me with 3 log 2 minus log 5. And then I'm going to get the x isolated by dividing. And then it will always ask you to express as, well, in log form, not as a decimal. Okay, so we're going to express in log form our answer because that is exact. And so we're going to put back together using log laws. So if I'm putting it back together, any exponent is coming back up. So this 2 goes back up, this 3 goes back up. So it'll be log 5. Okay, so the 2 is coming back up, so it's 2 to the power 2, which is 4. And then the 3 is coming back up, so it's 2 to the power 3, which is 8. And then we're going to change multiplication to addition. So it's 5 times 4, which is 20. And subtraction is going to become division. And so this is my answer. It's in log form. I don't need to change it to a decimal, only if it asks me to. This is an exact answer in log form. Okay? If I decided to put my x's on the other side, I'll show you what happens. Okay, so let's write the question out again. We'll do it. So we had 3x log 2 minus 2 log 2. And then we had x log 5 plus log 5. So let's say I decided to put the x's on the right. So I'm going to leave this here, bring over the log 5, and then I'll bring the 3x to the right. So I'll factor out the x on the right. And then we'll divide. And then we'll put it back together. Okay, so this negative 2 is going to come up. It's an exponent. This 3 is going to come up. So remember that that's going to be log 2. It's a bit messy. That's going to be log 2 to the power negative 2. I'm just going to write an extra step in here. And then that's 2 to the power 3 is 8. So keep in mind that 2 to the negative 2 is going to give me 1 over 4. And then subtraction becomes division. And then I'm dividing 1/4 divided by 5 is 1 over 20. Right? The 5 gets multiplied by the 4 because it's being divided. So when you look at your results, you'll notice that If I put the x's to the left in the numerator, I got log 20. In this way, I got 1 over 20. And then I got log 8 over 5, and here I got log 5 over 8. So if I put the variable to the other side, all that happens is that I get the reciprocals. And when I type both into the calculator, I would end up with the same decimal value, right? So they both have equal value. It's just that depending on which side you isolate your x, you might get the reciprocal in the log, okay? But it's fine. Both of them are the same. You'll get the same answer when you type it in through your calculator. Okay, are there any questions on that so far? Okay, I'm going to give you one question to try on your own, and then we will check and make sure everybody knows what they're doing. I'll just make one up. So let's okay, let's try that. So why don't you try to solve for x? You want to isolate for x in log form. I'll give you a couple of minutes to do that.